Hi everyone, I welcome you to this lesson on areas under the graphs. It's an application of definite integration. In this lesson, we'll learn the various methods used in finding the areas under the graphs above the x-axis. To start with, we are looking at the left endpoint method. In this method, we find the left endpoint of the rectangles that we want to approximate the area under the graph. So these left-hand points are onto the graph, and that's why this method is known as the left endpoint method. In this problem, we are finding the area under the graph from -4 to +1. As you can see that this will be an approximate area calculation because this part is not desired to be a part of the area because we want to find the area under the graph. So this area is what we are willing to find. But in these methods, we'll have to add these areas or we'll need to because we have no choice. And in this case, as you can see that sometimes the areas can be added and sometimes they will be eliminated or they won't be calculated. So as you can see that this part can compensate this, although this is less and this is more, and this part can compensate this, but then there will be a larger area which will be. So we can expect the approximate area with the help of this method to be a little bit more than the exact area. So let's get started in finding the area. So we need to find the coordinates of these points. So the left-hand points. So that is -4, and when we substitute -4 into our equation, so y when so we get the y value of 11. Now we can find the y value at x is equal to -3. So y when x is equal to -3. So the y value will be 6. So -3 comma 6. Y when x is equal to -2. Similarly, when x is equal to 1, -1. And when x is equal to 0, the value is 3. So these are the coordinates. Now, as you can see that we will only get 5 rectangles and the left hand points will be onto the graph. So the area of the first rectangle, let's say this is A1, will be equal to, so the width of these rectangles are the same, that is 1, because we need to keep it a little bit simple. We need to have the same width. but the heights are changing. So changing to 11, so area 1 will be 11 times 1. So the height of the rectangle length times width, so that will be 11 times 1 or 11 units. The area 2 will be equal to 6 times 1. Area 3 will be 3 times 1, or we can say that will be 3. The area 4 will be 2 times 1, which will be 2, and the area 5 will be also equal to 3 times 1 is equal to 3. Therefore, the approximate area will be equal to 11 plus 6, and that should be 25 square units. So with the help of left-hand point method, we get the area of 25 square units. And that's how we calculate the area under the graph with the help of left-hand point method. The right-hand point method is similar to the left-hand point method. The only difference is that we have to calculate the right endpoints because the right endpoints of these rectangles will be onto the graph. So as per the graph, the coordinates of the endpoints will be and the gap between the strip width is 1. These are also known as rectangular strips, and the width is equal and it is uniformly equal to 1. Therefore, the areas will be, so it will be the height is 2, so 2 times 1 is 2. And this is 1, this is 2 again, this is 5, and the last one is 10. So the total area calculation will be 2 plus 1 plus 2, that is 5 plus 5 is 10, 10 plus 10 is 20. So the approximate area we can expect to be 20 square units. And this is how you use the the right endpoint method to find the area under the graph. This area is expected to be higher than the exact area. So area will be higher than exact the area. And the reason why this area will be higher than the exact area is because you can see that some of the unwanted portions, they are larger than some of the portions uh, that are eliminated or that are not taken into account. So that's why the area of by this method in this problem will be a little bit higher than the exact area. So this is the right endpoint method to calculate the areas. In this next example, we have to calculate the area under the graph with the help of trapezoidal method. In the trapezoidal method, the area is calculated with the help of finding the areas of the trapezium. So as you can see that although you may not be able to see very clearly some of the lines, but you can see that very clearly that we need to find the points onto the graph and then find the area of trapeziums like this and then add them all up. This method is more accurate as you can see because the unwanted area is very less. So as you can see that it will be a little bit higher. So this method is calculating a little bit higher value than the exact values, but the unwanted portion is very, very less. So the area calculation will be more accurate in comparison to the left endpoint and the right endpoint method. So we need to find the endpoints. The graph is going to give us a very good help. It is going to help us to find the y coordinates. So that point should be, sorry, that was not 0, 12, that was negative 2, 12. So after finding these endpoints, we need to find the areas of these trapeziums. So let's say this is area A1. So area A1 will be, according to the trapezium rule, to find the area, the formula is so if you have a trapezium like this is A, this is B, and the gap between them is H. So even in this problem, the gap between the strips is 1. So therefore, the height H will be 1. So all we have to do is to find 12 plus 7 times 1 divided by 2. So that's the area A1. That's 19 over 2. Similarly, we continue to find the area A2, and that will be 7 plus 4 divided by 2. Area 3 will be 4 plus 3 divided by 2. Finally, we have to, so approximate, we need to add them. So the approximate area comes out to be 27.5 square units. This is how you calculate the approximate area with the help of trapezoidal method or trapezium method. Now moving to the exact area, Newton provided the method to calculate the exact area. In this method, we have to create the strips, and with the help of strips, we will be able to calculate the exact areas. But before we jump into this, let's go and explore the left endpoint method and the right endpoint method. Again, with the help of GeoGebra. The reason why we are exploring this is because if we increase the number of strips, right now the number of strips to find the area is 6. And you can see that each one of these is onto the left hand point. So this is the left hand point method to find the approximate area. The exact area is given by the integration, and the approximate area is given by the left hand point method. As you can see that the approximate area is a little bit more than the integration. The reason is that these unwanted portions are added with the help of approximate area. So if we increase the number of strips, the area will become very, very close to the exact area. So right now the number of strips are say 3. So the approximate value is 21.6n, which is a lot higher than 18.13. We increase the number of strips so that the unwanted area calculation will be less and less, and therefore it will become closer and closer to the exact value. So just to observe that if we increase the number of strips, then the area will become closer and closer to the exact value. So at 100 strips, you can see that unwanted calculation is lesser and lesser, and so therefore the approximate area becomes closer and closer to the exact area. And this is what computers and calculators use. This is the numerical method to find the approximate area with the help of left endpoint method. Right. Now the same thing with the right endpoint method. So in this case, I've got a graph x squared plus 1. And if we increase the number of strips, you will be able to see that the area will be closer and closer to the exact area because the unwanted calculation will be less and less. So only a little bit of part of this will be, and that's how you calculate the right endpoint method. If you increase the number of strips, the exact area calculate, so it will be approximate to the exact area. And this is the important thing which I want you to see. For the trapezium method, As we increase the number of trapeziums, you can see that with the help of integration, right now the area is 9, and just if we have just one triangle, and so this unwanted area is added, and the area of this triangle is 13.5, and that's why this unwanted area, this is unwanted area, and so that's why the area is a little bit higher. So if we increase the number of trapeziums, you can see that area becomes dramatically close to the exact area. So after say 34 subdivisions between 0 to 3, this area was very close to, became very close to the area, the exact area due to integration. Even the trapezium lines start becoming almost invisible. Okay, so as we increase the number of strips, you can see that the area calculation becomes more and more accurate. Now we're going back to our slide, and here I'm going to introduce the strip method to understand the area calculation. So Newton gave this method to find the area under the graphs. And he said that people were calculating the area with the help of rectangles like this left hand point method. So what he said is that if you decrease the width of the rectangles to such that the width becomes infinitely close to 0. So what he said is that if we have this width which is infinitely close to 0, so this width is dx, and this is nearly equal to 0. Then the height of this width will be y, and that will be y equals to f of x. Then the area of this rectangle strip will be, so area of the strip be y times dx, length times width. So y is the height, and then dx is the width. So height times width, or we can say it will be f of x times d of x. Integration means addition. Integration means to put it all together, to combine all together. That's the meaning of integration. So therefore, the area will be equal to from A to B. So we want to find the area from A to B. If we add these rectangular strips of the infinitely small width, then we get the area. So that means the area calculation can be carried out by doing f of x times dx from A to B. And that's how we calculate the area. You can also notice that the y values will be above the x-axis. That's how we calculate. We have designed the coordinates. So to calculate the y value, we have to go above the x-axis, means above the origin, uh, above or below. So the y values multiplied by the d of x, which is the width of the strip, and that is extremely small, close close to zero. And then when we sum them up or add them up with the help of integration from a to b, always the left hand point should be here, and this is the right. So when we add them from left to the right, that is a to b, so always the bottom should be a and the right part should be b, and that should be at the top of the integral. And this is how we calculate. In the same, but also I would like to mention that this area will be a positive area. Why this will be positive? Because the y values are positive. So y values are positive, therefore area will be positive. As simple as that. In the next diagram, you can see that the y values are negative. So if I make a strip here of infinitely small width d of x, so the width of this strip is d of x, and the y value, these y values are negative. So on calculation, the area will be negative. Because to find the area, we need to do y times dx. So the area of this strip will be equals to length times width, that is y times dx. And that will come out to be negative. Now the area from a to b will be given by integral, which is a to b. But then this area will be negative because the y values are negative. I think that's all in this lesson today. In the next lesson, we are going to explore and do some and solve some problems related to area calculation. I thank you all and wish to see you in the next lesson.